And now to our guest speaker, Dr. Harry Rowe, VP Geosciences at Premier Corex. Dr. Harry Rowe is Vice President of Geosciences at Premier Corex, where he leads the integration of advanced geoscientific techniques in support of global reservoir evaluation and stimulation design. With over 20 years of experience spanning academia and industry, Dr. Rowe is a recognized expert in scanning electron microscopy, geochemistry, and shale reservoir characterization. Prior to joining Premier, he served as a research scientist at the Bureau of Economic Geology at UT Austin, as an assistant professor at University of Texas at Arlington. Dr. Rowe holds a PhD in geological and environmental sciences from Stanford University and an MS in earth and planetary sciences from the University of New Mexico. All right, Harry, all yours.
Thank you, Dario, and thanks to everyone for joining today. All right, trying to share here.
There you go.
Is it working?
You betcha.
Okay. Yeah, today I'm going to talk about a value proposition. Engineers largely to set the scene here for Energy-Dispersive XRF. The acquisition of synthetic logs down the lateral is going to be a good substitute for quad combo logs that you generally have in the vertical. Usually don't see that in the lateral due to cost prohibitive issues. And then the integration and correlation of the rich vertical data sets, log to core, log to rotary sidewall core, and log to cuttings relationships with synthetic logs in the lateral variability can be related. And really what we're trying to get is mechanical properties or changes in mechanical properties along the wellbore. That's the value proposition and the perspective. After that, we'll talk about the facts and really go granular about the XRF method, reviewing all the parts of the XRF, what's important. It's a technique like any other technique that I want to show the warts and all. There are limitations, and really a lot of times the limitations, they're violated. And the key concepts that we want to talk about throughout this are consistency in analysis and interpretation, the accuracy of the analysis, and really just to look out for pitfalls. I'll give some examples of some fiction that I've seen, some fantasy, and some future prospects for Energy-Dispersive XRF. The value proposition. This is a generalized depiction of the rich data sets that we can get in the vertical. Wireline logs, core gamma, the core, and then paired analyses along this core that inform us about the strata and their mechanical properties, porosity, permeability, the geochemical properties as well, and the reactivity properties. It's also paired with rotary sidewall cores. These are very rich data sets and essential rock properties for constraining mechanical properties. But those in the lateral are prohibitively expensive to run these combo logs or to retrieve core. I have seen exactly 2 horizontal cores in my life. Very interesting, but also I would say probably not worth it for those companies to have taken those cores. A lot more information and can be gleaned, and that resource can be used in a different way for the creation of synthetic logs derived from the drill cuttings. So over here, we have the target zone. This is all just depicted in a very generalized fashion. But the cuttings along that wellbore and the log, we need correlation between these two. That correlation is very often provided, the initial correlation, because the gamma log can be reflected in the potassium, thorium, and uranium analysis of these cuttings. These cuttings serve as the ground truthing and a linkage to better constraints of mechanical properties. And integration of all of this information and modeling derived from these data sets provides a more predictive pathway for optimizing completions. Just to drive this home, this is a recent well we worked on. The gamma ray along the lateral here goes down into the Woodford, comes back up through the Mississippi Lime, and then into the lower Barnett. The ROP paired with that. Then everything else you see here is a synthetic log. EGR stands for elemental gamma ray. If you look down here in that Woodford, you see that there's some increases in the gamma ray signature here that are largely reflected in this EGR, elemental gamma ray, in here. The calcium, that's X-ray fluorescence, measures the elemental composition of rocks. And so I first plot calcium here, but very quickly, we don't all dream in calcium. We dream in calcite and quartz and clay. And so we have to convert this calcium to a mineral using stoichiometry. And most of the time in the rocks that we study, that calcium is in the form of calcite. It can be in dolomite and various other minerals, but calcium to calcite stoichiometry is very easily verified here. You can see the Woodford is very, very low in calcite. It's very common. It's much higher in clay here, and the clay is determined stoichiometrically using the aluminum, silicon, potassium, some of the other elements. And then quartz is determined by the leftover silica after forming clay. So there's a lot of chemistry, a lot of stoichiometry utilized here, and really underlying this is that link between XRF and XRD, X-ray diffraction, which gives you a mineralogy. If I don't say it again, really the tightness of fit between the elemental chemistry and the mineralogy is enhanced or really optimized when the very same powder that's analyzed by X-ray fluorescence then goes to the X-ray diffraction lab and is processed. So you're analyzing the exact same grains there. And this is a pseudo Young's modulus that my colleague Abhijit Mitra developed for this well. Anyway, the key here is that there's a rich data set to be had by generating these synthetic logs and comparing them to the existing log from the lateral, and then linking that back up into the vertical as well. This only works very well if the analysis is consistent and the results are accurate across the contributing data sets. Let me give you an example of inconsistency. An operator has worked in, let's say, the Delaware Basin on Wolfcamp A and B for 10 years. They used one mud logger for the first 10 wells. They used another mud logger the next 10 wells, and then, bounced around. Not only the mud loggers changed, but potentially the instrumentation changed, the calibration for those instruments, and the way the samples were prepped. 10 years later, a regional study might want to be undertaken. Good luck with that, with having that broad range of inconsistency across the people who generated those data sets. It's better to be consistent, and really it's best if you can be consistent and demonstrate accuracy at a good enough level. Energy-dispersive X-ray fluorescence, and in particular portable X-ray fluorescence. This is an example of all these instruments that are out there. Actually, this isn't all of them, but these were designed to provide people with numbers. They weren't necessarily designed to provide people with the right number. Very often, if you look at this readout, it will tell you elements that aren't even there. And if you don't know enough about how those data sets are being generated, you might want to use those data and use them way past the point of their actual accuracy or precision or anything else. So I just asked some questions here about really to draw question to utilizing these blindly. These handheld portable ED-XRFs have made a big impact in a lot of different sub-disciplines. The one we're really interested in right now, it's made a large impact over the last 15 or so years in the shale revolution. These are the elements, the ones in the solid red that we analyze routinely. So anything from sodium, that's the lightest element that we can measure with this instrumentation. Right? You know, there's some studies about fluorine, but fluorine doesn't really help us in the rocks that we're looking at, all the way up to uranium. We can measure uranium and thorium very, very well with a very high accuracy. There are some that I don't think that we can see. In fact, I know that we can't, but some people are starting to show things like scandium and these rare earth elements that we don't usually see in our line of work in the unconventionals, but these are very good as tracers in understanding where the rocks come from, and they're really not able to be quantified with this technique. There's a soft, very quickly hard line, and I'll kind of demonstrate why that is later. And this gets to the measurability of an element. It depends on the concentration, how intense the X-rays are. And so in general, these light elements, sodium, magnesium, aluminum, silicate, you know, their X-rays are not as intense because it's very surface centered or surface dependent measurement for those elements. They're very light elements that the X-rays are very weak and they can't get back up through the rock. So you're seeing what the sodium and magnesium are, aluminum are, very close to the surface. And then really the third one is our ability to deconvolute the complexities of the X-ray spectra. There's a lot of overlap in elemental responses that needs to be appreciated here. So just a backup 30,000 foot example of how powerful this technique can be. Several years ago at ERTEC, we presented this. There were 110 wells in the Delaware Basin that we analyzed from the Avalon down into largely the Wolfcamp A and B, a couple of Wolfcamp C's, but this is the distribution, the regional distribution of this, and all of these data points, 66,000 of them, generated the same way, generated with the calibration that we've been using since about 2009. And you see aluminum versus silicon. These elements may not mean very much to you, but aluminous phases are ones like clay and feldspar. And in the shale plays that we deal with, aluminum is dominantly in the clays. Aluminum means clay for the most part. And then silicon is in quartz, feldspars, and clays. So if you're high in silicon and aluminum, you're generally out here, and these tend to be clay-rich samples. And if you're high in silicon, low in aluminum, you're up here. This tends to be quartz-rich samples. So siltstones, sandstones, plot up here. And calcium, as I said, within calcite, they will, here's calcium versus silicon, low silicon, high calcium. These are where the limestones live up here. Again, these are all Delaware Basin and all Avalon down through about Wolfcamp B. So in general, I call this the triangle of truth because almost everything that we measure is right in that triangle. And really, the majority of what we measure is along a line right in here. That's where the thickest distribution of samples is. It's hard to see in these plots. There are dolomitic samples. They tend to plot here. They're still high in calcium, but they have more magnesium in there. And that's how we make the separation with stoichiometry. We take the magnesium to make dolomite, take the amount of calcium, and then remaining calcium goes to calcite. So that's how we make that transition between the elemental data that the energy-dispersive XRF gives us and the mineralogical data that are much more important and more widely utilized and understood by people. And why do we care about this? Well, rocks with a lot of clay tend to be more ductile in general. And then when they have high calcite or they have quartz and high carbonate, that tend to be more brittle. So built into this is an understanding of ductile to brittle relationships as well, which gets to the more important aspects for engineers, the mechanical properties. Imagine if this data set was generated across different laboratories, different users, people who had 6 days of experience versus 6 years of experience. It wouldn't look like this, and the reproducibility of it would not be there. The accuracy, the precision. These are the types of things that we worry about. If I'm a completions engineer, deep down inside of all that data set, everyone needs to understand consistency and try to test that throughout the process. And the chemistry is related to mineralogy. So that mineralogy change is interpretable as a change in physical properties of the rock, not a change in the shift or a change in a laboratory who's processing the samples. And very quickly, once a data set is generated, models start to be made. And this is one of those 110 wells, the data set. We make a chemophases model. This is very subjective, and the way I look at it is it useful to the geologist and others, or does it not go along with everything else that we know? And then very quickly, a brittleness model or a brittleness index, everybody has their own. And then mineral models. And the way to test the validity of a mineral model is to demonstrate what the XRD is telling us, a very high accuracy XRD. Those are the black dots here. Those are all XRD values across here. This is quartz plus feldspar, quartz, clay, carbonate, and calcite, and dolomite. And the colored regions, that's modeled mineralogy with the XRF, using an XRF to XRD model. So what you can see here is that we largely underestimate in this well, we underestimate the amount of dolomite here. So we have to go back and say, well, why aren't we making as much dolomite? Well, we're putting magnesium and iron and calcium into other phases. So those phases tend, and really the clay, we are overestimating the clay here. So we would go back and tweak that model and try to get this dot or these data sets to be through these dots here, and our model to better match the dolomite there. Or we could just move on, but you're always going to have this issue. It's better to kind of over time go back to these data sets and make modifications so that the next model would be predictive and ground truthing. Let's get real granular. How are these measurements made? Right. Every instrument has a CPU, signal processor, detector, and then the X-ray source here. X-rays come out of the X-ray source, excite an inner electron. That X-ray and that electron get married and fly away, leaving a vacancy in this orbital. An outer electron falls down to replace that electron, and in so doing has to give off energy to fall to that lower level. And that energy is in the form of a characteristic X-ray for this element. Every element has different characteristic X-rays, and that's why we can use this. If we look at inside this X-ray source, we have a cathode that's generating electrons that are flying rapidly toward this. It's either going to be a rhodium. There we go. Rhodium. There's all sorts of targets here. We use rhodium, and when this occurs, X-rays are generated. These X-rays get directed toward the sample, either the core or the cutting sample, and they produce characteristic X-rays like I just explained here. Something that's also not talked about is that there's an energy filter here, and changes in the voltage of the X-ray source. So the major elements are generally very easily excited with a low kilovolt X-ray source, and then we change that kilovolts to higher to excite the trace metals. And really, it's a technique of just optimizing this to optimize the excitation of the most elements under one setting. Measurements can be done in air, helium, and vacuum. We typically use helium, but some of the newest instruments are much more sensitive, and the air is pretty good. After about sodium or sodium and magnesium, that air analysis is pretty good. I like to get the best sodium and magnesium analyses, so I stick with helium. Talk about detector here, other than to say it's a silicon drift detector, and the advancements in these have been tremendous. The sensitivity and the peak resolution. So back when I started this using this technique, aluminum and silicon peaks were kind of conjoined, and now they're much more separated, so that we can get a much better analysis of aluminum and silicon, and then that can be attributed to better quantification of clays and quartz in sample. So, just in general, you have an X-ray source. These tend to be rhodium, silver, a full range. Rhodium is really good for rocks. It doesn't have to be, but it's best because that rhodium peak also comes into the analysis. At sample analysis, we excite with a broad range of energy. And this broad range you can see in the X-ray spectrum I'm about to show you. This is from the target. And then we also have the characteristic radiation from the rocks themselves. And you always saw these in your chemistry textbook. This is how all the electrons fall and the nomenclature. You don't have to know these at all for what you're doing, but appreciate that there's all sorts of electrons falling, and the energy associated with that can make an X-ray pattern very difficult to constrain. Ultimately, we want to get the right answer for these. Key to understanding everything, moving forward with an inter-element corrections, and understanding when there's contamination that overwhelms a sample. I'll give you an example: barite. If you don't get all the barite out, or if you don't get the majority of the barite out, it plays havoc, wreaks havoc with calcium, titanium, vanadium, lots of elements that people like to look at. So we really need to understand those inter-element corrections. We're not able to constrain them properly. You can see here barium. I don't have to show the peak, but barium lives around here, and titanium is right next door. These getting a good titanium analysis really depends on getting that barite down. Chlorine is another one. Everything that we drill out in the Permian and in the Williston, it's very high in brine, lots of chlorine. You need to get that salt out. Don't let it dry on the sample, because it will affect everything around this neighborhood. The rhodium is from the target. This is called the Compton peak, and we utilize this to normalize the spectrum. So messing with this by having a bunch of chlorine on it isn't good. In general, this is the 15 kV setting, so that we can measure from sodium all the way up to about iron. There's a couple of trace metals here that we have, but sodium is a very small peak here. We need to be able to measure that, so we measure it now for about 5 seconds. Used to be that we measure it for 3 minutes. That was 15, 16 years ago, but now 5 seconds we can get a good analysis on that sodium, magnesium. But we need all this to be clean and make sure that we're measuring the rock. Zoomed in on the baseline here. This is what the baseline looks like, and that's the result of that Bremsstrahlung radiation. A lot of this broad range of energy that's coming off that rhodium target hitting the rock. So you can see the characteristics X-rays popping up from it, but this is the Bremsstrahlung radiation. Bremsstrahlung just means breaking radiation. So I shouldn't say breaking radiation. Anyway, the different rocks have different patterns here. The granite, that Bremsstrahlung is a lot less pronounced here than in the shale, a lot less bouncing around of X-rays in the matrix. Here's the traces. So nickel, copper, zinc, gallium, all the way up to molybdenum. And then uranium is right here. It may look like we can't measure uranium very well because we have a lot of rubidium. It's a shale and lots of rubidium in shale. But the longer we count here, we can deconvolve a uranium peak from a rubidium peak. And that's pretty important when we're trying to compare the cuttings uranium with the gamma ray. Best practice, looking at that raw spectrum, understanding that there could be salts, barite, various contaminants that we need to get rid of, inter-element corrections or interferences I'll go over a little bit, and then yeah, that's it. These are two of our Egyptian colleagues still with the company. They do this technique in Egypt, the UAE, and even up in Kuwait. So we have a global footprint for doing X-ray fluorescence on cuttings and core. So we're doing it manually every couple of inches down a core, pretty good resolution. But what if we could use a core scanner? This is a core scanner with a spot size of about 3 by 4, and it's a contiguous measurement, about 101 samples per foot. This was a study that we did. We're trying to understand ash, mud rock intervals, and really most people doing this right now are focused on defining that linkage between the geochemical and mineralogical variations and how they can use that to predict the mechanical properties. Also, some of the fluid compatibility issues that are seen in these ash rich mud rock strata. This looks like great data, and this turned out to be a really good study. These are aluminum, by the way. And this is white light and UV light. It's the same rocks. It's about 8 feet of core, same box, but one's white light and one's UV. What's the problem with this? Number one, once you start the core scanner, it automates through this. So if it gets to a point where it's going through a salty interval, there's no way to just stop it, clean up the rock, and then tell it to keep going. There's no way to make it go back and redo this without redoing the entire box. So be very careful when you do core scanner studies. Ask for the raw data and ask for a demonstration that the chlorine and the sodium are very, very low and it's not impacting the surface scans. This is a study in the Illinois basin of a CCUS study, just demonstrating that we can generate very high resolution records. Now this is the first 2 feet. So this interval here is this interval right here in the core box. So you can see all sorts of variations and really, you know, can attribute all sorts of changes in the mechanical properties of this rock at a very small scale. But it comes at a price if it's swimming in brine. It's a cleaning problem here. I'd say labs get around this by not reporting chlorine, you know, and not reporting sodium variations that could easily be attributed to salt variation. And for this rock, you know, where is the chlorine? This is a micro XRF technique that I've used just to demonstrate that the chlorine content is highly variable across the face. This is just a couple of inches across here. And what you see is that it's just in little pockets. The red is the high chlorine. This is just on a scale from 0 to 100%. So, you know, cleaning this can be very, very difficult. And it generally occurs where there's the highest porosity in the rock. Calibration. This is the key distinguisher of labs is how are the calibrations made and how much do the people know about the inter-element correction. So the expectation and hope are that the reference materials mimic or match the unknown sample. And you know what I've done in the past and what we still do today is we generate reference materials from the formations that we're going to be analyzing for the most part. So our working calibration has Woodford, Barnett, Wolfcamp, has the Bakken, has Haynesville and Eagleford in it. So these are the pellets that we utilize. These have been around for 16 years, and I'll show you the results from these in a minute. But the matrix effect is a real effect. If you use granites or basalts or some other mud rock that really doesn't look like these chemically, you're not going to get the right answer, but you will get an answer. This is a great paper demonstrating that an all rock calibration versus an ultramafic calibration. Ultramafics are deep rocks kind of from the mantle or asthenosphere that have a lot lower silica, high magnesium and iron. But see the difference between these calibrations? That's the ultramafic, and this one is the all rock calibration. Highly variable, and if you notice, most of the time neither of these calibrations are actually on the 1-to-1 line, and that's something also that we look at. Getting a good calibration requires a good broad range of elemental concentrations, inter-element corrections knowledge, and an appreciation of the limitation. So this is our calibration, but it's our calibration on 4 instruments. All of these instruments are 8 years old too. So it's not all of our instruments, but all that we did this for. So sodium accepted, this is an ICP-MS value versus the value that we get when we take our 41 pellet calibration and apply it to all the samples as unknowns. Sodium, you can see it's kind of sausagey. That's the lightest element, and it's kind of difficult to get tight measurement, but this is pretty good for samples that are less than 2% sodium. Once we get to magnesium, everything's pretty good here, up to over 8%, nicely along the line, except for one sample here. And then aluminum, silicon, potassium, calcium, they're not going to show all of them. Molybdenum, which is an element that people use to define organic richness, and then uranium. So this is what is achievable across different instruments of the same type, very tight calibration. Another one, we an instrument from someone else. It's a Titan made by the same company, but this is what it looks like. Sodium's not as good, but by the time you get past magnesium and into aluminum, very, very good. Okay. On in here. 4 instruments plus that 5th Titan here. Very tight calibration, except for one there. And to kind of dead horse, that core scanner that I showed you earlier, we did the calibration for that. And again, everything nicely fits along here. Imagine that you had 100 wells with 100 data sets, all analyzed by the same instrumentation, or even a variation here, but with the same calibration. To be able to go back and relook at all these data sets, maybe do a regional study, and wouldn't immediately be confronted with the inconsistencies of it. Incidentally, this also looks really good because the same 2 physicists designed all of these instruments. So the same concepts carried themselves through these 6 instruments. The thing to look at is day-to-day reproducibility. I don't see this plotted by a lot of other folks, but this value here, 0.5% sodium, is the ICP-MS value for one of my references. And we run this reference on every instrument, everywhere on the planet that we have an instrument, every day before we start. And this is the day-to-day reproducibility of it. Okay, we run it 3 times, right? And that average is 0.54. So I am 0.04% off with sodium, okay, with a standard deviation of 0.03. For magnesium, this is the right answer. And this is the answer I get for this one pellet, one of the 41. You're always going to be off a little bit because you're just looking at one pellet. I just decided to pick one. And this is the precision. And you just judge the accuracy here by looking at the accepted versus that average value there. Silicon, we're a little bit low on this one. We always have been. There's nothing that I can do to correct it to get it back up there to that line. But it is very consistent. And of course, there's another pellet that's a little bit on the other side of the line, of that 41 pellet calibration line. Potassium, calcium, so pretty good. We'll save this for the geologist. Getting some data versus getting the best data. This is some studies that we do. We shoot from the hip, lay out some cuttings, and just scan some cuttings. The issues that we immediately deal with are salt. And what I would suggest is if you want really good data, never scan the cuttings. If you want to kind of just see where you are and understand it as a geologist, this is an okay technique. Otherwise, stay away from scanning rock. Various reasons. The salt reason is one of them, but look at these 3 cutting samples. This is a largely homolithic or similar lithology through here, largely dominated by shale. This is the pellet that's generated. This little diagram here is the X-ray beam, and this is the pellet that we make. Look at this significantly heterolithic sample here. It really depends on where you make the measurement. Here, there's a couple of big chunks of calcite or limestone underneath there. Lots of limestone on this one. So your spread of analyses, if you were to just continue to move the beam around and scan different parts, the percent calcium and aluminum and silicon that go into the calcite, the clays, and the quartzes are going to jump around a lot. It's best to make a pellet that is a representative sample of everything you see here. This is driving this point home. Is that this percent calcium versus depth? These are individual cutting samples going in the lateral. The dark gray dots here, that's just scanning cuttings. This is a pellet. And what you find in this type of lithology is the pellet is generally lower in calcium than everything else or most of the samples that are measured here. It's because the calcite creates a dust that coats everything, and it overestimates how much, over quantifies how much calcite and calcium is in there. So we don't dream in calcium, like I said, we dream in calcite. If we convert that calcium to calcite, these are the big changes that you might see. Let's take this sample. That's the pellet, representative sample from this. All of these sample cuttings analyses are up here. So what number do you want? Do you want anything from 48 to 72% calcite? No, this is the right answer for that interval. It's a very dangerous thing, just scanning cuttings. All right, same thing here. This is a Northern Delaware Basin chemostratigraphy from Lee County, just demonstrating the black are, I don't show the points, but in general, the black is constrained a lot more. Those are the pellets. And then the scanning of the cuttings are a lot jumpier in here. What happens too, and look at sulfur here, this is a very pyrite-rich interval, and these pyrites are probably they're old cuttings. So some of that sulfate has made it, sulfide got oxidized, made it to the surface, and you have these sulfate crusts. That's right at the surface. The XRF makes it over quantify how much sulfur is there. Highly variable. Better to make a pellet. I'm gonna running out of time here, so I'm gonna cut through the XRF to XRD modeling here, but understand that we're largely utilizing simple stoichiometry of minerals to convert XRF elemental chemistry into a modeled mineralogy. And the thing that I like is using the 1-to-1 line. If I fall off the 1-to-1 line, like I am here with feldspars, there's higher feldspar quantification with XRD than what I have when I model them. I need to do something to these data here. All of these points here, or most of them, are ones that fall above this line in the clays. I need to take some of the aluminum, potassium, and silicon that I've made clays with and turn them into feldspars and bring them up onto that line. So it's something that's easily done. I'm just demonstrating that the process that we go through to do this. These are small minerals, rutile or anatase, but we can change those to make them fall on the one-to-one line and where it makes sense, and do it in a very valid way. So very quickly, I want to talk about fiction and fantasy. I talked about scandium earlier. Scandium is one that some folks are saying they can measure. In general, scandium occurs in the low ppm concentration in the rocks that we look at. It also occurs right here on what we call the calcium K beta peak. So here's calcium K alpha and calcium K beta. By the way, this is a Smithwick shale with about 1%, little less than 1% calcium. This is the kind of rock that you might expect that you could actually see it here, but you don't see a peak for scandium. These instruments will give you a value for scandium, even if it's wrong. What I did was spike this shale with various amounts of scandium oxide. So I spiked it with a 2000 ppm scandium. That's what a 2000 ppm scandium looks like. By the way, average Earth crust has 22 ppm. So it's buried underneath that calcium peak, all the way down to 316 ppm. So that's over 10 times the amount that we really ought to see in this rock. And sure enough, that this red line here is our shale. We're not able to see any scandium. You know, I've spiked it here, and there's just no way that we can see that element. So anybody who's trying to tell you there's scandium in this rock that they can see, they can't by this technique. One is rare earth element. Not going to be utilized by engineers as much, but the geologists utilize these for tracer, really provenance studies. And these are the types of studies where people have been brave enough to demonstrate what they think they can measure. This is ICP-MS, the gold standard for elemental analysis. And here's the lanthanum for XRF. It is, again, what value do you want? For this value that this sample has, you go anywhere from just over 200 to just over 300 ppm for that sample, 5 analyses of the same sample. This technique cannot measure, cannot quantify these elements using a typical portable XRF. This can be done with energy-dispersive XRF, but skip. You have to use a much larger, much more powerful X-ray fluorescence. It's still energy dispersive, but you have to put it in a room. It's not portable. And this is kind of where we are now with the rare earth elements. As we can see, lanthanum, cerium, praseodymium is hiding underneath here, but you can deconvolve it with some software all the way up to a terbium. Can't get lutetium. But this technique of a larger XRF, much more powerful, over 100 kilovolts, we can do this. And my hope is that we kind of see this kind of get a lot more use in the geological studies, especially for provenance. Skip through these, summarizing that value prospect that we had. You know, imagine here's your acreage. You have a science well here with a beautiful log suite, maybe even some indentation measurements. A lot of cool relationships can be developed from maybe not nano indentation, but some of these meso indentation measurements, and coupling those to the XRF analyses, physical properties, everything on this science well, a couple of rotary sidewall cuttings wells, and then the cuttings wells that are start to generate here. All of the data from all of this can be put in through machine learning model. This is the way to really start to chip away at how to develop this acreage, but it has to be done consistently. That elemental geochemistry is relevant to geologists, but it's really not relevant to the engineers. What makes its relevance is the synthetic logs and how these can go into telling us a lot more about what's going on in the lateral as far as mechanical properties. I'll also say that this work should be done in a lab. the work being done out in the field. It can be useful, but it's generally the data have to be generated very quickly. And unfortunately, with speed comes a loss of consistency and accuracy. And really, these data have to be guided by the petrophysicists, data scientists, and engineers. For a lasting thought, the main one that I want to say here is if we want to more from our data, and you will in the future, especially if you look back and try to reanalyze something to gain predictability or ground truthing, we need to place greater emphasis on the technique consistency and archiving the measurements so that we can go back and understand where the errors are. Thank you. I'll leave it there.
Well, thank you, Harry. That was a lot to process. Talk a little bit about the cutting samples, repeatability. How many points would you want to do? I know you showed an example where the well cuts through like 3 or 4 different formations, which is probably quite typical. But to take us through the process of the sampling and testing, repeatability, that sort of thing.
Yeah. Some things like repeatability are pretty forgiving. We're dealing with samples that are pretty homogeneous on a small scale, but when you cut across different lithologies where you have limestone shale, or limey shale, or shaly lime, or we call them marls, it really, you can get whatever you want as far as an answer between those two lithologies. So you have to make a decision of, do I measure both lithologies, or do I combine this for this interval? And I think for your purposes, combining it, as long as you're not going over a very long interval. By very long, I mean tens of feet, probably. When my discussion with Dante, he's suggesting, an analysis of about every 15 feet would be really good for the kind of things he wants to do. And there, very often you'll find cuttings from operators that are more on the order of 20 to 50 feet. And so I think we do need to up our speed of analysis. But we'll get a bucket of cuttings. The key thing that we do is try to wash them as much as we can. It's not a difficult process. It's just Dawn dish soap and water. But everything that's on that surface that's not the rock really bugs our analysis. And that barite, if we don't get rid of it, it just comes back to bite us later on. So I think I just hit a whole bunch of things, but maybe didn't hit everything that you wanted there, Dario. But cleaning the sample and making sure we're analyzing the rock is the most important thing, and that takes a while.
How long does the actual test? How quickly can you process a well?
Oh, a day or two, a couple of days. We can do 150 analyses in a day without breaking a sweat. Okay. Somewhere between, if we have extra shifts, we can do, a whole well or very close to a whole well. It's more in the cleaning. The analysis doesn't take long, but if you don't do those early steps, the analysis, you go back and have to clean more cuttings to get the right analysis. It's the barite more often than anything else.
That's from the drilling mud, the barite?
Yeah.
Okay. So Steve Cobb, also along the similar line with the synthetic logs you showed, approximately how many samples were measured and how long did that effort of cleaning, processing, and measuring take?
Oh, that was a couple of days. And I think that well had 320. That's all the way back through, but there's 320 analyses in here, maybe 340, and the resolution of sample selection changed. I think somewhere around here you can see it went from be 30 feet to 20 feet in the lateral here. But yeah, you want that kind of resolution. If you took out every other sample here, I think you'd be okay. But the economics of running these samples is so small compared to how much it costed to drill this well that the resolution that you have here is, I think it pays off.
So we can
for that analysis.
We can estimate a Young's modulus off of this. Is that correct? You show us.
Yeah, that's what
Abhijit did.
Abhijit has done here. Yeah, I'd have to refresh what he was doing here, but yeah, I can estimate Young's modulus using the results here.
Any idea on Poisson's ratio?
I don't know that, but yeah, I should, but
okay.
I think the main thing is that when you marry this to all those quad combos from the vertical and the sonic log and everything else, that some of these things can fall out as very, very good estimates of this. And of course, if one is going to be focused on Woodford and Barnett for the next 200 wells, this kind of, I think those types of relationships or ground truthing are going to show themselves in the first couple of wells.
So realistically, you're drilling your well, you're getting your cuttings. By the time they're done drilling, you get these samples to you almost before they're finished completing the well. Not talking fracturing or anything, but cementing and getting ready. You've already got this data potentially available to the completion engineer. I mean, like you said,
yeah,
you've got a number of wells that you're going to do. This just makes such sense to just go ahead and do it and be able to correlate from well to well just on simple cuttings tests.
Yeah, and I think the correlation and the are we in zone, those questions are certainly the ones that are asked more often. But I think there's a distinction here is that and a lot of those are asked at the well site, and a lot of those questions can be kind of demonstrated to a high percentage of probability that yeah, we're in zone, we're not in zone. But this really does take the analytical potential of a lab, the cleaning potential of a lab, and I think it can be drawn out more than just a correlation. It really is I guess I'm failing to come up with a word, but it's more than just a correlation. It's really demonstrating in a synthetic way through integration what the mechanical properties of the well are. And in my discussion with Dante, this engineered completions, I used to think of it as, well, we would change the staging. We would have one stage that's this length and another stage that's that length. And I think, what he was talking about was, no. We know a lot more about how to modify within a stage. And really just, we want to know where these rocks are changing so that we can overcome that by really some of the things that engineers do and understand much better.
Exactly. So from Michael Fonseca, for the more brittle rock plotted in the silicon versus aluminum plot, were you able to pair SEM microscopy on those cuttings, and do you observe any trends?
We did not have an SEM study of this, and so really, this was a regional scale analysis that really tried to demonstrate correlation and demonstrate that kind of what level of clustering we could get to that made sense, and log scale variations that we saw. But I would love to do something like that, but no, there wasn't a petrography and SEM analysis of these. Would have been nice.
Okay. And then from Robert Estes, Harry, you talked about drilled cores, rotary sidewall cores, and cutting samples. Do you see any value in samples from ballistic sidewall cores?
From what kind of sidewall?
Ballistic. So the percussion sidewalls.
Oh, I don't think that I've ever analyzed one of those. I could have, but are those taken in a very violent way? So that
Yes.
does that disrupt any kind of, yeah, so I would imagine like the rock mechanics information that you get might be compromised. The elemental chemistry, I don't really see a problem with, but yeah, if that's all you have, I think the elemental chemistry would be very good. Okay. And the mineralogy.
Yeah. And then the final comment from Islam Mitwali is, it'd be nice to see the correlation between the mineralogy model and high-resolution geomechanics model by Tavera. And he'd like you to talk to him. Comments on that?
All righty. I think there hasn't been enough done on the high-res geochem. I think we're still in the mode of, let's do high-res geochem to understand variability, and then let's take some plugs and put them in the triax and get some kind of rock mechanics and geomechanical model going. I think in talking to a couple of colleagues at universities recently, we can start to build something that's a lot richer at a small scale using nano indentation and kind of intermediate indentation techniques, ground truth it with some of the plug-based rock mechanics studies, but really that scaling between very small and macro scale, I think that's where this ought to go. And the pairing of the XRF with geomechanical studies, it's still pretty early on. That's the way I see it, but I don't inhabit that world enough to be very definitive on that.
Awesome. Thank you so much, Harry. That was, I think, very useful, very interesting, and really do appreciate your time to put this together for us. So thank you, and we'll see you soon. Reminder to everyone, next week we'll talk multi-frac completion, state performance evaluation with acoustic and thermal energy with Hugo Gavea. And if you're interested in being a guest speaker, please let us know. Contact us at nsitech.com when NSI Days, through LinkedIn, or at info@nsitech.com. And with that, I thank everyone for joining us.